The purpose of this video is to use Coulomb's law in order to do some calculation work. So here we go. So what is Coulomb's law? Well, it says that the magnitude of the electrostatic force is equal to K, the electrostatic constant, times the magnitude of the first charge times the magnitude of the second charge divided by the distance from center to center of those charges squared. So that the more out of balance each of these objects' charges are, the stronger the force between them, and the further away they are, the weaker the force between them, or the lot weaker because of an inverse squared relationship. So let's just look at a typical calculation. So let's say in our example here we have two charges, charge 1 and charge 2. Okay, 1 and 2. And let's say that the distance between them is 45 centimeters. Okay, and let's say that the charge on object 1 is, well, let's actually use a fairly realistic amount of charge. If I were to take my green strip and rub that with fur, that thing would get a charge on the order of microcoulombs. And so let's say that that's about like 15 microcoulombs. And we're going to use that amount of charge there because that's a fairly typical amount of charge. I get the benefit of seeing if you remember how to do the conversions, but I like using that sort of scale of charge because that's fairly typical. Let's say object 2 is also negative, and let's say that is negative 30 microcoulombs. All right, now the question here is, what is the force of 1 on 2? Okay, so the first thing I'm actually going to do here is figure out the direction of the force. These are both negative. That means like charges repel, and that means I'm concerned only what's happening to number 2, meaning the force of 1 on 2 is going to be repulsion, and that repulsion in this perspective is to the right here. Okay, so that is the force, the electrostatic force of 1 on 2. And remember that notation, 1 on 2. Now I put the FE in here. When we do these problems, we'll just actually probably skip the E there as well and just use something like 1 on 2 just because there's a lot of subscripts going on down there. So I'm going to use logic in order to figure out the direction, and I'm going to use the equation in order to figure out the magnitude. So FE is equal to K, right? 9.0 times 10 to the 9th newtons meters squared over Coulomb squared. Remember, we're just going to use the 2 sig fig version of it. The numbers get really annoying when you use 8.99, so do we really need to be that precise? We're not building bridges here, folks. Let's just make our lives easier. But the units of this do give us a really important reminder. Notice I'm about to plug in my two charges, Q1 and Q2, but I've got these in microcoulombs, right? So the first thing I need to do is remember what is a microcoulomb. Micro is times 10 to the negative 6th. The next thing we notice is that absolute value, I'm not plugging in the sign of the charge. So here we go. My next plug-in here is just 15 times 10 to the negative 6 coulombs. Now notice, that's not in proper scientific notation, but who cares? It's a plug-in. This technically in proper scientific notation was 1.5 times 10 to the negative 5th. And people screw that up all the time, putting this in proper scientific notation. So guess what? Don't, right? Only the answer has to be in proper scientific notation. And then Q2, once again, I'm not plugging in the sign, right? Because the signs don't tell me anything, because all I'm doing is calculating the magnitude here. And notice here I also didn't make a declaration. We're going to see a problem where we're going to use declarations in just a minute. The reason is because I've only got one force on here. I only need a declaration in order to know how to combine forces with each other. The declaration would not affect the sign of the charges, the flavor of the charges, right? Remember, this negative thing just means this thing has excess electrons. This thing has more excess electrons. All right. So here we go. This is the force of 1 on 2, and then the distance. Okay, notice meters squared, so I'm going to just convert that 0.45 meters quantity squared. So what are the common errors here? Let's just list them. First, screwing up conversions or not converting is probably the most important thing that people mess up with this, right? Knowing that this has got to be in meters, these have got to be in coulombs. They can't be in microcoulombs, they can't be in nanocoulombs, they can't be in elementary charges, they have to be in coulombs. Thing two, people plugging into the signs. The signs wouldn't do anything for you because a negative sign here doesn't mean like to the left or to the right. This negative sign means that this thing has excess electrons. That negative sign has nothing to do with directionality. So just because we use positives and negatives for directionalities along one axis, a single axis, doesn't mean that that's the only thing a negative sign can mean. So we have to be pretty careful with that. So here we go. This is also good practice for using your calculator, that magical EE button, because all these numbers are really, really big and really, really large in terms of our plugins. So there we go. And when you do this, you actually get a very nice answer, 20 newtons. So let's actually see if we're on the right order of magnitude. We can do an order of magnitude calculation, right? Remember that skill. So here we go. 9 times 10 to the 9th, that's actually pretty close to 10 times 10 to the 9th or 10 to the 10th. So I'm going to use 10 to the 10th anytime that I am doing that. This is going to be 10 to the negative 5th. This is 10 to the negative 5th. And this is over 10 to the negative 1st squared. Oh, okay, cool. So that all gives me 10 to the 0, and that gives me 10 to the negative 2. So this should be on the order of 10 to the 2nd, which is about 100. I'm not that far off there. It's on the right sort of scale. So we're just going to say that I'm probably in the right area there. So that's the electrostatic force of 1 on 2, and I'm actually going to take the magnitude signs off and say to the right, because I can do that with my picture there, know that to the right. I don't have to say declarations or whatnot here, because I'm being descriptive of what that direction is. So there we go. Now, what about the force of 2 on 1 here? Because 1 has a smaller charge here. So would 1 feel a stronger force? Hopefully no, I didn't fool you on that. It would be exactly the same magnitude of force. Why? The plug-in would be identical, but more importantly, Newton's third law demands that the force of 1 on 2 has to be equal in magnitude as the force of 2 on 1, but in the opposite direction. Remember, these things repel, so this would be the electrostatic force of 2 on 1. So, nice, simple problem there with electrostatics. And so you'll do a couple of examples of some of these nice simple problems. And then later in the week, we're going to kind of build it up, but I'm going to talk about some of these harder problems now, just so you can see it. So I kind of hinted at it before, but here we go. Let's say rather than just have 2 charges, I have 3. And I'll just put them in a line vertically like this. Let's say that this first charge, we'll call it charge 1, is at the origin. Charge 2, so like I'll just put this on a coordinate axis just so that we can feel a little bit more comfortable here. We'll say this is the positive y, that's the positive x. Charge 2 is at a position of 0, 4 meters. Charge 3 as a position of 0, meters, 5 meters. And let's say that Q1 is positive 10 microcoulombs, Q2 is positive 40 microcoulombs, and then Q3 is negative 20 microcoulombs. Okay, cool. So what is our question here? The question is, what is the net force on charge 1? That's what we want to answer. Now, notice here, we're only going to be dealing with the electrostatic forces. I didn't say anything about the masses of these objects because that's going to get a little tricky, because in general, when we're talking about charged objects, the electrostatic force tends to, on average, be stronger than the force of gravity. A little quick proof of that, in a previous video, I charged up a balloon by rubbing my balloon on the hair. I transferred like a bunch of excess electrons over onto the balloon. Not that many, like maybe a couple of billion excess electrons over onto the balloon. So that thing had a charge somewhere on the order of nanocoulombs. yet my hair stood up. Even though the entire Earth is pulling down on my hair, a couple of excess electrons on the balloon was enough to pull it up. So we're not going to worry about gravity in these situations unless you start seeing things about mass, and it'll become a little bit more apparent later. So what's the net force on charge 1? So the first thing we should actually do is do our force process. Step 1, free body diagram. So let's look at charge 1. What forces act on charge 1? Oh, well, 2 acts on 1. These are both positive, meaning that these two things repel. Awesome. So there it is. That is the force of 2 on 1. Okay? Oh, but 3 also acts on 1. These are oppositely charged. That means it's attractive. That means 1 gets pulled towards 3. I probably should draw it straight down, but I didn't want to do it over the same thing. 3 on 1. Notice both those subscripts are something on 1 because I only care about 1. While we're at it, let's actually just look at all of them just for fun. Object 2. Well, 1 acts on 2, same flavor, therefore it repels. So there is the force of 1 on 2. And how about 2 on 3? These are oppositely flavored, therefore it attracts. And so here we go. That's the force of 3 on 2. Down here, 1 and 3 are oppositely flavored, therefore they're going to attract. Therefore, 3 would get attracted towards 1. This is the force of 1 on 3. These are oppositely flavored as well, therefore attractive, therefore force of 2 on 3. Great, so now I only care about 1 for now, and then we'll come back to the others. So step 1 here was to do a free body diagram for any relevant mass. Step 2, directionality axes. I actually already put down axes here, so I've got that. Towards the top of the page is positive, towards the right of the page is positive. I already set that out prior to doing this problem. Step 3, write our knowns, kind of have all our knowns here. Step 4, side calculation, or actually step 3 would be drawing components for any non-axial vectors. I don't have any non-axial vectors here, so I don't have to worry about it. Step 4, side calculations. Here I have side calculations, right? I actually have to calculate the forces. So let's calculate the magnitudes of the force of 2 on 1 and 3 on 1. So that's K, Q2, Q1 over R12 squared. So I'll just use subscripts here just so, because R12 is not the same thing as R13, it's not the same thing as R23, right? It's always good to have good subscripts that tell a story. So 9 times 10 to the 9th newtons meters over Coulomb squared, Q2 right there, 40 microcoulombs, so let's put that in, right? And then we'll do Q1, 10 microcoulombs, excuse me. And how far apart are they? My parentheses is not drawing there. 1 and 2 are 4 meters apart. Boom. So we'll put that in and then squared. And then throw that into our calculator. 9 exponent 9 times 40 exponent negative 6 times 10 exponent negative 6, excuse me, divided by 4 squared. And we get 0.225 newtons. Okay, and then I've got the force of 3 on 1, and this is going to equal K Q3 Q1 all over R31 squared. So there we go. So actually, before I calculate it, would we expect this force to be larger or smaller than force of 2 on 1? Well, if we look at this, here the charges are 40 and 10 microcoulombs, here 20 and 10. So the product in the numerator is going to be less, so the force could be less. Oh, and they're further apart, inverse squared, this force is definitely going to be less, right, for both reasons there. So 9 times 10 to the 9th newtons meters squared over Coulomb squared, Q3, remember, just plugging in the amount of charge. I'm leaving out the sign because we're not dealing with signs here, because the signs don't say anything about direction except for the way we decoded it earlier, over 5 meters squared. All right, cool. So 9 exponent 9 times 20 exponent negative 6 times 10 exponent negative. I'm saying exponent, right, because the magic button on my calculator is the EXP button. Divided by 5 squared, and the expected result of 0.072, expected meaning it is smaller. So now I have it. Great. So now I want to know the net force, so let's bring this together. The net force on object 1. I actually don't care about the mass times the acceleration here. I only care about the magnitude of the net force, so I'm not actually going to write out Newton's second law in this case because it's not relevant. But I am going to use my declarations in order to do things. We said towards the top is positive. Both these forces are negative in that declaration, so I've got negative magnitude of 2 on 1 minus 3 on 1. There it goes. And so now I would see that my net force here is this minus this, or let's see. .297. That's within our boundaries. I don't need to put that in proper scientific notation. And remember, this means downwards towards the bottom of the page, right? To bottom of page. Awesome. So there you have it. I did that skill that we talked about before. So there we go with that. Now, I'm going to just for fun, I'm going to do the net force on 2. Notice here, if I want to do the net force on 2, I need the force of 1 on 2, but I know the force of 2 on 1. Awesome. So I can actually just start with, if I want to know F net 2 is equal to question mark, I know I need that F 1 on 2 has an equal magnitude to F 2 on 1, and that's because of Newton's third law. So I've already got that 0.225 newtons. But I do need to calculate the force of 3 on 1, right? Or actually 3 on 2 is the thing I want. So K Q3, Q2 over R23 squared. Or 3/2, it doesn't actually matter here, I'm sorry. I just keep doing that in numerical order for no particular reason. Can do these in numerical order as well. The order doesn't matter because, multiplication is commutative, right? So 3 is 20 times 10 to the negative 6. 2 is 40 times 10 to the negative 6 coulombs all over. Oh, and how far apart are they? They're actually 9 meters apart because of that. So 9 exponent 9 times 20 exponent negative 6, okay, times 40 exponent negative 6 divided by 9 squared is equal to, not a neat number like some of the others. Actually, we'll just go to out to the thousandths place there, and we will round it to 0.089, even though it's 0.88 repeating. Okay, cool. So now I've got that magnitude. Now let's construct our net force equation using our declaration. We said towards the top is positive. Oh, so that's going to be a positive. That's going to be a negative based on that declaration. So I've got a positive magnitude of F1 on 2 minus an F3 on 2. So we can then put that in. And so I've got F1 on 2 is positive 0.225 newtons minus 0.089 newtons, oops, I need parentheses there. And if I put that into my calculator, I get positive 0.136, and that positive just means to the top of the page, towards the top of the page. Okay, great. Now, let's kick it up a notch, shall we? Yep, yes we shall. We're going to use our same charges, but we're going to put them in a different orientation now. I'm going to keep my axes positive x, positive y, positive x. I'm going to keep charge 1 where it was, and it's the same charge at the origin. I'm going to keep charge 2 where it was. It is going to be at 0, 4, and it's got the same amount of charge, but now I'm going to move charge 3 over here, right? And I'm going to put it at 5 meters, comma 0, and it's going to have the same amount. So we know charge 1 is plus 40 microcoulombs. I probably shouldn't have written that there. Charge 2 is plus 10 microcoulombs, and charge 3 is equal to 20 microcoulombs. Okay, now I want to answer the same question again. What is the net force on charge 1? So let's draw in the forces. Free body diagram. This is 2, this is 1. The force of 2 on 1 is still in this direction, right? Because we didn't change anything about that. In fact, we actually already know the magnitude of it because we didn't change it. So the force of 2 on 1 is equal to the magnitude of it, 225 newtons. Now, the force of 3 on 1, we know that 3 is negative, 1 is positive, so it's attractive. So that means that it gets pulled in this direction, force of 3 on 1. Okay, oof. All right, got something different there. Now, the nice thing here is that the force is still the same magnitude because it's still the same 2 charges, and they are still the same distance of 5 meters away. So we've already got that, so it's 0.072 newtons. But what's true about the net force on this? I can't add these together like that because they're on different axes. So what do I have to do? Well, when you have your force on different axes, what you have to do is, if you remember back to the beginning of the year, we need to find the resultant in the x direction and the resultant in the y direction and then combine them. So what's the net force x and what's the net force y, and then combine them. So that's pretty simple here because if we look in the x direction, there's only one force in the x direction, that's in the positive x direction. So in the positive x direction, F of 3 on 1. Right? In the y direction, there's only one force, and it's in the negative direction, so the negative F2 on 1. Okay? So we could do that, construct net force equations in each direction. And so what would that look like? Well, positive 0.072 newtons and negative 0.225 newtons. Now, what do we do with those? Well, we know that the magnitude of the net force is going to be the square root of the sum of the squares of the components of the resultant. And so that is then 0.072 newtons, quantity squared, plus this, which is 0.225 newtons squared. And so I put that in my calculator. 2 plus 225, okay, square root of quantity. And that gets me 0.236 newtons, but that's not enough. I need to know the direction of that. Well, where is that net force? Well, if I've got a force pushing down and a force pushing to the right, the resultant's got to be somewhere in between those two forces when drawn concurrently, or I have to draw them consecutively, so move this one over here in order to do tip-to-tail addition. Either way, I would get that this is the direction of F net on object 1. And so remember, I have to find out what that angle is on that net force, right? So theta 1 net, I will call it, just because we want to keep our notation consistent. Remember here, I'm just looking for the reference angle. So that's always the vertical part of it. So F net, the magnitude of F net y over the magnitude of F net x, right? This is all stuff from the first unit, right back the 8th, 9th, and 10th days of class, okay? And so we could put that in our calculator, 0.225 divided by 0.0. So notice these are magnitudes because remember, I'm just finding a reference angle. Our tangent, answer 72.3 degrees, good. So I have my final answer, F net 1 is equal to 0.236 newtons at 72.3 degrees below positive x. And now I have a full answer to that. Great. So remember, another way we could have done this is we could have done a table of goodness, if you remember the table of goodness, right? And so this would have been F of 2 on 1, F of 3 on 1, and then F net. And this is x and then y. And I would have said, oh, here, this has no x component, this has no y component. This has negative 0.225 newtons, and this is positive 0.072 newtons, and then come up with these quantities using the table. So you can either construct sum of force equations in each dimension or do the table of goodness. All right, let's just do one more with these, and then we'll call it a video. So how about the net force on object 2? Okay, well, we know that the force of 2 on 1 is going to be up in this direction, right? Because they are both positive, so they repel. 2 and 3 attract. Oh, geez, what direction do they go? Well, they always go on the straight line between them. Boom. So that is the force of 3 on 2. Couple of problems here now, folks. I know force of 2 on 1's magnitude. It's the same as before. Actually, this should be 1 on 2, excuse me. I know that because it's the same, but I don't know this anymore because in our old situation, 3 and 2, where we're 9 meters apart, now they're not. So looking at this geometry, it looks like the new R23 is equal to the square root of 4 meters squared plus 5 meters squared, or it's going to be radical 16 plus 25, 41 meters. Now, I'm not going to actually find out what that number is because remember, when I go into Coulomb's law, I'm going to square that. So having radical 41 is actually going to be pretty easy. But let's walk through our process. Step 1, free body diagram for the thing that matters. Step 2, we know axes and declarations, that's fine. Step 3, draw in components. So I have a non-axial vector now. F3 on 2 is non-axial. So I have F3 on 2 x and F3 on 2 y. So that's F3 on 2, okay? Oh man, I need to know what that angle is there. I'll call that angle 3 on 2. Oh, darn it. So I don't know that either. And I don't know the components yet. So, oh, I got it. I can get this from the geometry. If you notice, this angle here is alter interior with this angle here. And that would mean that theta 3 on 2 has got to be, and there's no, like, this is how you do it always, folks, for these types of problems. You just have to recognize what angles you need and then do the coordinate geometry to work, right? Notice I've got a right triangle here, and so I can use this right triangle now in order to find out what that angle is. And it looks like I can do the arctangent of that distance there, which is 4 meters over that distance, right? 5 meters. And so the angle that 3, 2 makes with the horizontal is then the arctangent of 0.8. And so the arctangent of 0.8 is equal to 38.7 degrees. Okay, so I'm going to take all that and now do some work. So our next step in the process after drawing components is finding anything that we need to find. So we already know F1 on 2's magnitude is 0.225 newtons. Remember, that was our Newton's third law argument, but I do need to find a new F of 3 on 2 based on the new geometry between those two charges. So this is the R32 squared. So that's going to be 9 times 10 to the 9th newtons meters squared over Coulomb squared. We know charge 3 is 20 times 10 to the negative 6 coulombs. I just ignore the negative sign once again. 10 times 10 to the negative 6th all over. And this is where I take my radical 41 meters quantity squared. So I can just have radical 41 on the bottom after I square that. So that was a little shortcut there. Because sometimes then if you make decimals, then round those decimals, you just introduce unnecessary rounding into your problem. And so we might as well try and preserve some lack of unnecessary rounding. So there, newtons. Now the next thing I'm going to want to do is I'm going to want to find out what the components then. So F3 on 2x is equal to, well, looking at that, F3 on 2 is on the adjacent side of this right triangle here. So when you're on your adjacent side, remember you do the magnitude of the thing times cosine of the angle of the reference angle. 0.44 newtons. Cosine of, what is that again, 38.7 degrees. And so here we go, times cosine of 38.7 degrees. Okay, I just messed something up putting in the calculator, times cosine of 38.7 degrees, and that's going to be 0.034. I'm just going to keep everything rounded to the same amount here so I don't have like artificial precision where it doesn't belong. So sine of 3.2, right? Remember, don't memorize x is cosine, y is sine. That's not true. That's not true. It's about look at the coordinate geometry. Cosine goes with the whatever component's on the adjacent side, and sine goes on whatever's on the opposite side. Okay, so just keep that in mind. That's what you should be memorizing if you're memorizing anything process-wise. Okay, 0.0. There we go. And now I'm going to do it with the table of goodness this time. I know I've got two forces, F of 1 on 2, F of 3 on 2, and then F net 2. So here we go. What do I have here? F1 on 2 goes directly upwards, so has no y component. Let's go back to the free body diagram, right? Has no x component, excuse me, and the whole thing is in the y direction, so I can just put the whole thing there. Now I go F3 on 2, the x component of this, there it is in the positive x direction, so I plunk in a positive 0.034 newtons. The y component of 3.2 is downwards, so that's a negative 0.028 newtons. Therefore, I can get the components of the resultant, the net force, right? That's just equal to that. And then this is also going to be positive, so 0.225 minus 0.028 is 0.197 newtons. Therefore, now I can find the magnitude of the net force on object 2 is the square root of the F net 2x squared magnitude F net 2y squared magnitude is equal to, plug it in, 0.034 newtons squared plus 0.197 newtons quantity squared. Throw that in your calculator, boom, plus, boom, is equal to square root. Yeah. Okay, this pretty much comes out to 2.00 newtons. It's actually 0.11999, so to 3 sig figs, that's what we got. And then if I want to know the reference angle for that, that's going to be the arctangent of, once again, the magnitude of the y component over the magnitude of the x component. So arctangent of 0.197 newtons over 0.034 newtons. And that gives us a value of 0.034. Second tangent, answer 80.2 degrees. So if we look at that, that's positive x to the right, positive y up. So in other words, my final answer here is F net 2 is equal to 0.200 newtons at 80.2 degrees above positive x, because this puts me solidly in the first quadrant based on what I have there, meaning this force is really big, that force isn't. If I was to look at the two of them, just a little side drawing, drawn concurrently, we know that the resultant has to be somewhere in between them, but since this force is so much bigger, it skews much more strongly to this force than to that force. Actually, it's going to be a little bit smaller. There it is, at an 80-degree angle there. Okay, so there's our process. It mirrors the process that we did earlier in the year. I'm bringing back all the vector fun. I say vector fun, you probably say vector hell, but welcome there.